everyone, and welcome back to the Whale Nerds podcast. This is mini episode number 12, Minisode 12. This time around, we're going to talk a little bit about how sound moves in water. So we talk a lot about whale acoustics and communication underwater. We reference the Monterey Bay Aquarium Research Institute hydrophone quite often. It transmits live on the internet through the Mimbari website. And so I just kind of wanted to give everyone a bit of the basics of how sound moves through the ocean, because it is different than air and it affects how whales and dolphins communicate with one another, along with a lot of other ocean creatures. A lot of what we actually know about acoustics in the ocean comes from the campaigns from different navies around the world, especially the United States, to detect submarines underwater. So there was a lot of effort made to put hydrophone arrays in the oceans to detect submarine movements. And it was actually all kind of a military project at first. And those people that were working at those stations started to realize that they were hearing all kinds of ocean sounds. And they did have to catalog them all because they needed to know what was biological and what was potentially man-made sounds in the ocean to help them better defend their coastlines. So a lot of what we know comes from the U.S. Navy and their SOSUS stations, which you'll see, you'll hear me reference throughout the article. And it's pretty cool stuff, the way that sounds move through the water. And hopefully at some point, we'll have a few people on throughout the podcast that work in bioacoustics. So you can always come back to this episode as a primer as to like how sound moves in water, and just kind of refresh your brain when they're talking about frequencies and wavelengths and the deep sound channel and all that kind of stuff. You'll have a reference of what all those things mean. So you can always come back to this episode for that. I also just finished Roger Payne's book, Among Whales, and he was like one of the first researchers to do recordings of humpback whale song underwater. So he does talk a bit about ocean acoustics, and so I just wanted to like kind of share a little bit of what I learned. He has a really good reference section at the end of his book that goes over a lot of this information too, but I'll give you the sources as I go for all the information I'm going to share with you. So the basics of ocean acoustics, this first set of information is coming from the National Oceanic and Atmospheric Administration, or NOAA, their Ocean Explorer page. They have an article about ocean acoustics. I'll link that on our Facebook page when we post about the episode. So basically, sound is vibration, right? So for us, when we hear sound as humans, we're detecting pressure waves moving through air. So it's the same for water. Underwater objects vibrate. They create sound pressure waves that alternately compress and decompress the water molecules as the sound wave travels through the ocean. Sound waves radiate in all directions away from their source, like ripples on the surface of a pond. The compressions and decompressions associated with the sound waves are detected as changes in pressure by the structures in our ears and most man-made sound receptors, such as a hydrophone or an underwater microphone. The basic components of a sound wave are frequency, wavelength, and amplitude. We use those three terms to define sound. So frequency is the number of pressure waves that pass by a reference point per unit time. And that measurement is in hertz, or cycles per second. To the human ear, an increase in frequency is perceived as a higher pitched sound, while a decrease in frequency is perceived as a lower pitched sound. Humans generally hear sound waves whose frequencies are between 20 and 20,000 hertz. Below 20 hertz, we define those sounds as infrasonic, that's INFRA, sonic, infrasonic, and above 20,000 hertz, we define those as ultrasonic. Just if you are into music, the frequency of a middle C on a piano is 246 hertz, if that helps frame what range we can hear in. So frequency is the number of pressure waves or cycles per second, and that measurement is called hertz. a wavelength. So these are pressure waves. So just like you could see waves on the ocean as the water is moving, the distance between two peaks, so between the two high points of waves right next to each other, that's called the wavelength. So how long is the wave? And it is related to frequency because they're inversely related. So a low frequency sound has a long wavelength. So big wavelength, low frequency. Small wavelength, high frequency. So short wavelength, high frequency. So that describes, so far we've described how fast basically and what's the distance. And then amplitude, this describes the height of the sound pressure wave or the loudness of the sound. And it's measured in decibels. So small variations in amplitude, so short pressure waves, those produce weak or quiet sounds, while large variations, tall pressure waves, produce strong or loud sounds. This one's kind of tricky to like wrap your brain around, especially because decibels is measured at a logarithmic scale. So it's like a J curve if you look at a chart. And so the decibel scale is logarithmic, used to measure the amplitude of sound. If the amplitude of sound is increased in a series of equal steps, the loudness of the sound will increase in steps which are perceived as successively smaller. A decibel doesn't really represent a unit of measure like a yard or a meter, but instead a pressure value in decibels expresses a ratio between the measured pressure and the reference pressure. So we have set the reference pressure as like 0 is like no sound, right? So it doesn't go as a 1-to-1 ratio as it increases. So that's why it's kind of complicated to explain amplitude and how to measure in decibels. It's a function of power. And so on the decibel scale, everything refers to power, which is amplitude squared. And just to confuse things even more, the reference pressure in air is different from that in water. So like you'll hear people try and compare like the sound of a blue whale to like the jet engine of a airplane. And like it's really tricky to like kind of get into that math. So like 150 decibels in water is not the same as 150 decibels in air. You're kind of describing how a sound wave behaves when you're describing the amplitude. And then sound waves behave differently in water than they do in air. So decibels and amplitude, that's always the one that I struggle with. I usually talk more about frequency and about wavelength because those are easier to visualize for me. But you can also kind of look at different charts and things, and that can help you maybe understand what those measurements look like and what that means the sound wave looks like, which is weird because you're hearing it, you're not looking at it, but you can look at it. Anyways, so the speed of a wave is the rate at which it's vibrating through the medium that it's in. So sound moves at a speed of about 340 meters per second in air. That's what we humans are used to listening to. But water is a much thicker medium. If you remember, if you happen to listen to the competitive group episode, I talked about how water is about 800 times thicker than air. So the mechanical properties of those two mediums are different, but it actually turns out that sound moves way faster in water because like the next molecule is close together to move the sound along. So sound moves at about 1,500 meters per second in water. So that's 4.4 times faster than sound moves in air. So almost 4.5 times faster sound through water than it is through air. Temperature also affects the speed of sound. So sound travels faster in warm water compared to cold water. And that actually is a big deal in some parts of the ocean. And then you have to remember also that wavelength and frequency are related to this whole thing, because the lower the frequency, the longer the wavelength. And the wavelength helps you measure the speed of the sound. The wavelength of a sound equals the sound of speed in either air or water divided by the frequency of the wave. So a 20 hertz sound wave is 75 meters long in the water, but a 20 hertz sound wave in air is only 17 meters long. So it's moving differently, which then also affects the speed and the length of the wave. So then there's this feature in the ocean. I was talking about how temperature plays a big role in this. So there's this kind of natural phenomenon in the ocean that creates this thing called the SOFAR channel. So sound in the sea can often be trapped and effectively carried very long distances by the deep sound channel that exists in the ocean. The SOFAR, or sound fixing and ranging channel, is so named because it was discovered that there was a channel in the deep ocean within which acoustic energy from a small explosive charge could travel over long distances. An array of hydrophones could be used to roughly locate the source of the charge, thereby allowing rescue of downed pilots far out at sea. Sound, and especially low frequency sound, can travel thousands of meters with very little loss of signal. So to kind of frame like why this happens in water, so within the ocean, the speed of sound varies with changes in depth, and that accompanies normal changes in temperature and pressure. Specific combinations of temperature, pressure, and salinity may act to create shadow zones or reflective layers that are resistant to the propagation of sound waves. A specific set of conditions, however, also create a channel through which sound waves propagate at minimal speed, but with minimal loss of strength. Similar to the transmission of light through a fiber optic cable, the refracting or bending of sound waves by layers of water with varying temperature, pressure, and or salinity allow the formation of a well-defined sound channel. So remember, it's slower, but it doesn't lose energy. So long wavelength sounds are going to do well in this steep sound channel. This new information is going to be coming from a website called waterencyclopedia.com. Although the oceans are not uniform bodies of water, there are currents of water with dramatic variations of temperature, such as the Gulf Stream in the North Atlantic, and salinity. The speed of sound in these deeper regions of the oceans is influenced more by high pressure. At shallower depths, temperature plays the most dominant role in governing the speed of sound. The greater the temperature of water, the faster the sound travels. Surface temperature variation can be significant, with seasonal variations in the amount of sunlight that can produce changes in the near surface temperatures, which then turn to affect the speed of the sound in water near the ocean surface. When the near surface layer is well mixed by currents and surface action, a resulting isothermal layer allows uniform propagation speeds for sound waves. Such isothermal layers are common in mid-latitude regions. So kind of those like halfway points between the poles and the equator, which is where we do see a lot of whales feeding. The surface water tends to get mixed enough that the thermocline kind of stays stable. So a temperature gradient exists when the temperature of water decreases as you get deeper, and this is called a thermocline. The resulting thermocline shows a characteristic decrease in the speed of sound with decreasing temperature. So it gets colder, sound slows down. However, at a depth of approximately 750 meters, that's about 2,500 feet, the variations in temperature become so slight that the water becomes essentially uniform temperature. From that point, the speed of sound is regulated more by the changes in pressure that accompany increasing depth. So once you get to a certain point underwater, the temperature doesn't change very much, but the pressure does. Because the sound wave transmission speed is directly proportional to pressure, because remember, sound's just pressure waves that our ears know how to turn into information. Because sound wave transmission speed is directly proportional to pressure, the speed of sound increases as the pressure increases with depth. So speed of sound gets faster as the pressure increases in deeper water. So there's this kind of sound pipeline or deep sound channel within the ocean that allows the transmission of low frequency sound over thousands of kilometers. This whole thing was discovered in 1943 by an American team led by Maurice Ewing and J.L. Wortzel, and independently by a Soviet physicist named Leonid Brikoskov. I don't know how to say it. I'm sorry. Basically, they were able to determine that there was these properties in the deep sea that could transmit low frequency, long wavelength sound, because they picked up the detection of an explosion near the Bahamas on hydrophone receivers stationed off the coast of Africa, so across the Atlantic Ocean basin. So the SOFAR channel depths are also kind of a function of the depth and thickness of the thermocline. So wherever that like ideal temperature range starts in the deep ocean is where that SOFAR channel is going to be. So it's not like this one uniform, big, long layer in ocean water. It does kind of move around a little bit. So the deep sound channels are closer to the surface in cold water and then deeper down in warmer water. Temperature and pressure affect water density as well, and that will affect the refraction of the sound waves in those different layers of water. You could basically think of like, if you don't really know how fiber optic cable works, it's like you could visualize like a straw, and like somehow you are able to only transmit a sound or light through this straw, and the straw is just like letting the information ping pong back and forth up and down the sides of the inside of the straw as it carries that information down like a much more defined path. So instead of just like yelling out loud, you're like only yelling into the straw, and then that's keeping that sound contained in that little straw until it gets out the other end. So basically the SOFAR channel like traps the sound. That's one way to put it. And when they're traveling at a minimum velocity, the sound waves lose very little energy. So this can allow certain sound waves to propagate over distances in excess of 25,000 kilometers. That's like 15,500 miles. So to reference, like, okay, so they detected the explosion off the Bahamas with a hydrophone off of Africa. The Atlantic Ocean is anywhere from 2,800 to 4,800 kilometers wide. So the sound could have traveled another 20,000 kilometers potentially. So the Pacific Ocean is about 20,000 kilometers wide. So this is saying the right conditions and the right sound wavelength could travel further than the Pacific Ocean's basin. So you could hear things definitely across the ocean. Before the widespread use of GPS, this was actually used to help navigate for marine vessels. And some scientists have hypothesized for a long time that whales utilize this to communicate over long distances. So what does this all mean for whales? I mean, they definitely can hear each other across the ocean, right? Like at this point, there's no question. They definitely can hear each other across the ocean. There was another article about someone who's working with people that use the SOSIS system. There's a pretty well-known bioacoustics guy named Chris Clark who works at Cornell. And so there's this article that the Cornell Chronicle published back in 2005 where he's just coming off of like presenting at a conference. And so they're kind of talking to him about, you know, studying whales and their sounds, using the SOSIS information. And at this point, it was still kind of like a newer thing to use this. Now, a lot of people know this information in the marine world and have used these different recordings to make all kinds of cool scientific discoveries. But basically the article starts with, instead of being used to track Soviet subs as they move through the Atlantic, the underwater microphones of the Sound Surveillance System, SOSUS, can track singing fin, blue, humpback, and minke whales. From acoustical maps that Chris Clark and his colleagues have attained, they have come to realize that we've been thinking about whales in the wrong time scale. There's definitely a time, he says, there's definitely a time delay in the water, and the response times for their communication are not the same as ours. Suddenly you realize that their behavior is not defined by a human scale or any other whale researcher scale, but by a whale sense of scale, an ocean basin size. We know very little about whale communication. That is why we're looking for patterns of association and coordination. The problem is that whales are spaced so far apart. So you think about, sound still travels 1,500 meters per second, but then you're asking, how long does it take for that sound to go all the way across the ocean? Like, what if the whales are 2,000 meters apart, or 2,000 kilometers apart? How long does it take to receive that sound, for the whale to understand where it's coming from, what it means, and then make a sound back, and then that sound to get back to that other whale? So we now have he says, we now have evidence that they are communicating with each other over thousands of miles of ocean. Using SOSUS, Clark can move a cursor around a screen and listen in on different areas of the North Atlantic. If he hears a whale singing, he can fix its location and position in space and time and observe animals that are tens of miles apart, cohorts of humpback whales moving coherently, and watch the collective migration of species in large portions of the ocean basin. He says, so for example, if I'm a whale off Newfoundland, I can hear a whale off Bermuda. Whales also will aim directly at a seamount that is hundreds of miles away. Then once they reach it, change course and head to a new feature. It is as if they are slaloming, like, skiing, the slalom race thing. It's as if they're ping-ponging from one geographic feature to the next. They must have acoustic memories similar to our visual memories, is his conclusion based on his work back then. I can't remember if we talked about this on a podcast episode or if this was me and Slater like rambling on the phone, but when you think about like where whales go to breed, a lot of times they're islands or seamounts in that area. Some of them are active geologically still, like Hawaiian Islands. They're active volcanoes. They're still making sounds underwater all the time as the volcanic activity is growing new islands out of the Pacific Ocean. The Caribbean, there is still some activity around those, but just the sound of islands in the middle of the ocean as well has a unique acoustic signature. So I really do think that they listen to that stuff and that makes a significant enough noise that they can help figure out where they're going. Like, I think sound plays a way bigger role than we realize because whales are very acoustic creatures. When you think about just the limited visibility based on the depths they use, the phytoplankton and other plankton loads in the water, cloud cover. I mean, what's the one thing that they'll never be deprived of in the ocean environment that they can use as a reliable signature to navigate? And it would be sound. Like, you can't rely on light when you live in water. That's just not like, yeah, there's a pattern and a routine to the sunlight of the day, but like in Monterey, we don't see the sun for weeks at a time because it's cloudy. And then also there's plankton. So like you can't see more than a few feet. So you might have good eyesight, but like hearing is how you figure out your life. And so I think that plays a way bigger role than people realize. And also for humans, it's like really hard to understand what the whales are experiencing because our ears are not built for water. They're built for air. And that's a whole different time scale of receiving information. And then because we do have visual cues that take over a lot of our information gathering as we navigate through our day, we don't rely as heavily on sound as whales do. And so it's just like, it is kind of its own little world down there. And since we're not built for that, even when we go swimming, like we don't understand what the whales are experiencing. And so it is hard to measure, and it's hard to like conceptualize, to study it and ask the right questions, because like our brains aren't made for it, which is kind of crazy to think about. So hopefully that was more helpful than it was confusing, because I always personally struggle with explaining things that I can't visualize very well. I mean, like that I did this part of this episode was for me to better understand and refresh myself on how sound is basically energy and how it moves through water and how you measure it. So hopefully that's helpful to you, and you can always come back to this and reference this if we're talking to a guest who's talking about bioacoustics, or if we're talking about a paper that has to do with whale communication, anything like that. And if you can't find the links to this information later on, you can always email us, whalenerds@gmail.com, or send us a message on Facebook or Instagram. We're at Whale Nerds, and I would be happy to send you the links to all this information. We always archive it, so we have it available. You can also follow along with us on social media, or you can follow along on our website, which is thewhalenerds.com. Keep up with what we're doing, what we got going on, latest episodes, trips, merch, all that good stuff. And thanks so much for listening.